Good morning to Professor Suhaimi. My name is Keong. I'm from SEMT 3212 Flight Mechanics. Today, I would like to present my assignment 4 on aircraft static stability and performance. The material and apparatus that I use are Manila cut, cutting mat, paper cutter, ruler, steel tape measure, pen, cellophane tape, stick, and bolt. The dimension of my paper aeroplane is B equal to 0.25 meter, CR equal to 0.06 meter, and CT equal to 0.04 meter. The location for me to conduct my flight test is my room with calm air at home. I made two paper aeroplanes. The first one is paper aeroplane without ballast. Second one is paper aeroplane with ballast. I use both as the ballast. My boat weighs 4 grams. I conduct the flight test 10 times for both paper aeroplanes. Below is the video of flight test for both paper aeroplanes. For paper aeroplane without ballast, the center of gravity is determined by using a pen. CG is 3.5 cm from leading edge. The mean aerodynamic chord is 0.0507 meter. The aerodynamic center is 0.022 meter from leading edge. The Cm alpha W of this paper aeroplane is 1.151 per radian. Therefore, I can conclude that the paper aeroplane without ballast is statically unstable. This is because Cm alpha W is more than 0. The stick fixed neutral point is 0.022 meter. For paper aeroplane with ballast, the first condition I need to consider is the CG point need to be less than SC point, which is 0.022 meter. So, the location of ballast need to be less than 0.01225 meter. Therefore, I place the ballast 13 mm in front of the leading edge. The CG point of paper aeroplane with ballast is 0.00757 meter from leading edge. The Cm alpha W is negative 1.2698 per radian. I can conclude that paper aeroplane with ballast is statically stable. This is because Cm alpha W is less than 0. During the flight test, I observed that paper aeroplane with ballast fly with stable condition and gliding manner. The stick fixed neutral point is 0.022 meter. After the 10-time flight test, the average speed of paper aeroplane is 3.0468 meter per second. The lift to drag ratio is 3.4557. The lift coefficient is 0.969. The drag coefficient is 0.2803. The trim speed is 3.0424 meter per second. The power required is 0.0607 watt. The power to weight ratio is 0.8839. The drag polar equation is CD equal to 0.1906 plus 0.0933 CL squared, where K equal to 0.0933. The error coefficient is 3.7495. For horizontal tail, according to United States Air Force Stability and Control.com, the position of horizontal tail needs to be 60% of body length. I assume the body length is 100 mm. Therefore, the position of horizontal tail is 60 mm. The horizontal tail volume coefficient is 0.5. The horizontal tail area is 0.00528 meters squared. Assume the aspect ratio equal to 4, then B will be equal to 0.1453 meter. Assume also the taper ratio equal to 0.5, then CT equal to 0.5 CR. From the horizontal tail area, I can get CR equal to 0.04845 meter, CT equal to 0.02423 meter. After adding horizontal tail, the new CG point is 0.0233 meter. To check the stability of the paper aeroplane, equation below will be used. CL alpha T equal to 4.1888 per radian. VH equal to 0.6682 meter per second. dE over d alpha equal to 0.7143. By inserting these values, Cm alpha equal to negative 0.6846 per radian. With this horizontal tail, the flight will be statically stable because Cm alpha less than 0. For the vertical tail, which is fin, the vertical tail volume coefficient is 0.004. By using formula of vertical tail, the area of vertical tail is equal to 0.0020833 meters squared. With this vertical tail, it can maintain the directional stability of the aircraft. For an aircraft with positive dihedral angle, it is obvious that the aircraft will be more stable than aircraft without dihedral angle. When aircraft is flying, lift force acts perpendicular to the relative airflow. If the aircraft rolls to the side when it is disturbed by a gust of wind, the lift vector links to the side with the aircraft. This creates a resultant sideways facing force that makes the aircraft side slip in the same direction. As a result of this side slip, the aircraft is subjected to a sideways component of the relative airflow. Due to dihedral, the lower wing meets the upcoming relative airflows at a greater angle of attack than the upper wings. Consequently, the lower wings produce more lift and helps the aircraft roll back to its original position. In conclusion, the paper aeroplane without ballast is statically unstable due to the position of CG point is behind the AC point. The paper aeroplane with ballast is statically stable due to the position of CG point is in front of the AC point. For a statically stable aircraft, Cm alpha must be less than 0, which indicates that CG point must be in front of AC point. That's all from me. Thank you.